Me. Um, I'm very happy to be here. The EAI Academy seminars are usually a very nice series of presentations, and I'm glad that I can be a part of it now. So today we will talk about Enceladus and Europa because I believe they are very compelling targets for the search for life beyond Earth. Um, on the left here, you can see Saturn's moon Enceladus. That's a very bright object. The surface ice is made of relatively pure water ice. In the northern hemisphere, you can see quite a few impact craters here. In the southern hemisphere, there are not that many impact craters, but there are these four nearly parallel cracks in the icy surface, the so-called tiger stripes. On the right here, you can see Jupiter's moon Europa. That looks quite a bit different. The surface ice is not that bright as Enceladus, on Enceladus. You see these reddish, brownish colors that are indicative of some kind of surface chemistry. So other things than pure water ice are probably there. And both moons, they have one thing in common beneath these ice shells, and that's a global liquid water ocean. So we know that they are not the only object in the solar system with liquid water. There is also our home planet Earth, as you know, with water at the surface. Then I mentioned Enceladus, Europa, then there's Titan, that's another moon of Saturn, and Ganymede, that's another moon of Jupiter. And then we are relatively sure there's also an ocean on Callisto. And there's some evidence for other objects in the solar system that I marked here with a question mark. Some evidence for liquid water oceans, but this still needs to be confirmed. For example, Neptune's moon Triton or Dione, which is another moon of Saturn. And one interesting fact is that if you compare how large these worlds are, and then you see relative to that volume the amount of liquid water on these worlds, you can see that actually there's only a drop of water on Earth compared relative to the overall volume of Earth, and there's a lot more water on Enceladus, again, relative to the moon's total volume. Yeah. So, and by that definition, as an ocean world, all these objects fulfill one requirement for the origin of life as we know it, and that's liquid water. So we also need some kind of energy, for example, in the form of sunlight, hydrothermal activity, radiolysis, photolysis, or whatever. And then you also need some interesting chemistry. You need the right elements so that the chemistry over a certain amount of time can hopefully turn into biology. And if we now plot all these objects that I've shown in the previous slide into this diagram, you can see that actually there are three moons that appear to fulfill all these three requirements. And that's Europa, Enceladus, and Titan. And then Europa and Enceladus, they have one advantage over Titan, and that is they have a rocky core that is in contact with the subsurface water ocean. So this is a potential source for heat and interesting ongoing chemistry in the interior of the moon. Titan, in contrast, probably has a liquid water ocean that is sandwiched between two layers of ice. So the ocean of Titan is very likely not in direct contact with the rocky core underneath. So let's talk a bit more about Enceladus. The Cassini spacecraft was launched in 1997 by NASA and ESA toward the Saturn system to investigate the planet, its moons, and rings. The most remarkable feature of Saturn is probably this amazing ring system. So there are these inner moons, these denser rings, and then there's one bright, very diffuse ring, the so-called E-ring. And when Cassini came closer, you could see that Enceladus actually orbits Saturn in the brightest spot of this E-ring, of the E-ring. So there's a kind of connection probably between Enceladus and Saturn's E-ring. And Cassini came even closer, and then it discovered these remarkable plumes. So there is some kind of material that is ejected into space from the interior. And it turned out relatively soon that this material actually comes very likely from the subsurface liquid water ocean. And then the instruments on board Cassini were pointed toward Enceladus and did more and more measurements to find out more and more about that moon. And another thing, when Cassini came very close to the moon. It took these pictures of these four tiger stripes. They're named after four Arabic cities. And then Cassini also found that Enceladus emits a huge amount of energy into this from the south polar region, actually from this region where the plume is emitted. You can maybe get an idea if you compare the average surface temperature, which is about minus 200 degrees C, with the temperature at the tiger stripes, which is about minus 80 degrees C, which is still incredibly cold. But if you compare these two numbers, that's a difference of 120 Kelvin, and that's huge for such a tiny moon. Enceladus is about 500 kilometers in diameter. So the total amount of power output on Enceladus in the South Pole region is about between 5 and 20 gigawatt. So putting together what we know from the interior of Enceladus, what we think to know, there's a rocky silicate core. Then we have the aforementioned global liquid water ocean that interacts with the core through hydrothermal vents, very likely. And then the outermost layer is the ice crust. So with a varying thickness. So the ice crust in the South Polar region is probably only around 5 kilometers, maybe even a bit less thick. And in other regions of the moon, the thickness can be up to 30 or 40 kilometers. And then, as mentioned, there is this plume that emits material from the ocean into space. And these cracks in the surface connect the ocean with space. Basically, allow the material to travel from the ocean to space and get emitted. The plume is composed of gases and ice grains, much more gas than ice grains, with a ratio of ice to gas ratio of about 10% by mass. And of all these ice grains that are emitted, about 90% of these grains, they cannot escape Enceladus gravity and they just fall back to the moon. And about 10%, they get emitted and enter Saturn's E-ring. And that's why Saturn's E-ring looks that diffuse and bright, because it is mainly made of these particles that come from Enceladus ocean. And one of the instruments on board Cassini was able to analyze these ice grains. This worked in a way that a single ice grain is hitting the instrument's target, that's a metal plate, and then gets partially vaporized and ionized, and the instrument was able to measure cations, so the positively charged ions that get generated just by the impact of the ice grain onto the metal plate. And with that, you can get you can record mass spectra and get compositional information of what is actually in these ice grains. And when you get the data back from space, you need experiments in the lab to calibrate what you actually see. And one such instrument is situated in Berlin, where we have used a tiny liquid water beam that is hit by a pulsed infrared laser. And due to the laser energy, you create a plume of ions and macroscopic fragments, and the cations, so the positively charged ions, and the anions, the negatively charged ions, could be measured with the same technique that was employed by the mass spectrometer on board Cassini. That's time-of-flight mass spectrometry. Here's a very short video how it looks like when the laser beam hits the water beam. So each bright dot here is one shot of the laser onto the water beam. And here this tiny hole here is basically the entrance gate to the mass spectrometer. And then with this lab experiment, together with the data from Cassini, there were many comparisons made. So you have the data in the lab, you have the data from Cassini, and then you can try to compare this and make sense of it. So here's an example. On the left, you can see a sodium poor ice grain that was recorded in Enceladus vicinity. And on the right, you can see a mass spectrum recorded with this lab setup, where we have reproduced what Cassini saw in this ice grain. And in both cases, you can see that the same species are created in very similar relative abundances. And then we can, based on this analysis, we can categorize ice grains that were emitted from Enceladus. So on the one hand, there is so-called type 1 ice grains. That's mostly pure water ice, pure water plus some traces of salt. So it's not a surprise, there's water. Then for now, I will skip type 2 and go to type 3 already. That's the salt-rich ice grains. So there's a lot of salt in these ice grains. Most notably sodium chloride, sodium carbonate, bicarbonate, and also phosphates. So you may know sodium bicarbonate from baking soda in the kitchen, or sodium chloride also from table salt that you probably use in the kitchen. And then there's another type that I just skipped, that's type 2, and that's also very interesting for if you want to search for life on Enceladus. That's the organics-rich ice grains. So on the one hand, we found organic material in these ice grains. This is believed to be relatively large, means above 200 atomic mass units. Concentrations are in individual grains on the percent level, and these organics probably have a variety of functional groups and are poorly water soluble. On the other hand, there are low mass organic molecules. Concentrations can vary, and they are mostly aliphatic and have polar functional groups that are water soluble and probably volatile. So I want to emphasize that the structures I show here, it does not mean that exactly these compounds have been found on Enceladus, but the features that we find in the data would be in agreement with these compounds. It's extremely difficult to really pinpoint a specific compound and tell and say, yes, exactly this has been found and exactly this is what the mass spectrum shows us. This is just to illustrate examples what might be there on Enceladus. So putting all this together, again, we have Enceladus hot rocky core that interacts with the global water ocean and eventually emits material from the ocean into space through the plume and its south polar region. The water ocean is salty. We have these salt-rich ice grains and contains organic material, a variety of organic material. Some of this material is likely to be dissolved in the ocean. Some of this material is more likely to form a tiny layer of poorly water-soluble organic matter on top of the water table. And through a variety of processes, this material can get ejected into space and then detected. All right. So now we talked about Enceladus and sorry. And now I also want to talk about Europa. So here in white, you can see what we actually learned from Galileo Galilei in 1610. So you see this white circle, that's Jupiter. And then there are these four stars. He called them the Medicean stars. And it turned out that these are the four large moons of Jupiter, the four Galilean moons. There's the innermost moon, that's Io. This is the most volcanically active body in the solar system. Then we have Europa, Ganymede, and Callisto, all of which appear to have liquid water oceans. And the innermost three moons are in a so-called Laplace resonance. So meaning that whenever Ganymede does one orbit around Jupiter, Europa does two, and Io does four. So this means that these moons actually meet always at the same spot in space. So there's always a gravitational tug at the same location in space on these moons, giving a kind of energy to these moons to maintain the ocean liquid, for example. Yeah, some information about Europa. Europa is bigger than Enceladus. It probably also has a rocky interior and we know there's a global liquid water ocean that can maybe interact with the rocky interior. And then there's the ice shell on the top. And an important thing for Enceladus is if there's actually a mechanism to bring material from the interior to space so that we can analyze it, one possibility would be plumes. there is some indication of plumes on Europa, but this still needs to be confirmed. Then we can think about such kind of upwelling interior ice structures. Then maybe in the ice shell we have some water pockets with very high salinity solutions. Then there is a kind of subsumption or subduction ongoing. So on Europa's surface, ice is subducted under denser ice into the interior. And if you look at the surface, then you can see here these cracks that you can find at the global scale. So Europa is a very active body. And the surface ice is mostly made of H2O ice. And endogenous carbon was recently found, which is quite interesting. Endogenous means actually that it probably comes from the interior, and there is some kind of mechanism to bring that stuff from the interior to the surface. And this is we are talking about carbon, which is very interesting for the search for life again. And then there's likely sodium chloride at the surface and maybe some other compounds, mostly oxidized species. And these interior processes are very important because they would allow us to bring material from the interior to the surface, and then we could maybe analyze material from the ocean. And these processes are also important for another reason, and because Jupiter has a very strong magnetic field, and Jupiter emits many charged particles all the time, and Europa is bombarded by these particles all the time. So whenever these charged particles hit the surface, some chemistry can happen. So for example, if there are interesting molecules, they can break down or they can react to form other molecules. We don't really know that yet. And such an environment is very likely an oxidation environment, while on the other hand, any scenario that we can imagine of a seafloor that interacts with the water ocean is probably reducing. And if there are these exchange processes, then we can maybe get a redox potential on Europa, which is again very interesting for life because life as we know it on Earth relies on such redox potentials. So this would be a very good source for energy. And we don't know as much about Europa as we know about Enceladus, but this will change soon because NASA has already launched the Europa Clipper mission in October 2024. I was actually very lucky to be there and watch that launch myself. Here's a photo that was taken by a colleague of mine who was there as well. There you can see the Falcon Heavy rocket with there was the spacecraft on board. That was just a moment when the spacecraft was launched. The big mission goal of Europa Clipper is to explore Europa's habitability using 9 science instruments on board the mission. Europa Clipper is complementary to other missions, for example, ESA's JUICE mission that is also on the way to the Jupiter system, and also complementary to a potential future Europa lander. Because if you send a spacecraft to Europa, like Europa Clipper, you can take advantage of it and scout for potential landing sites where you could land maybe at some point in the future. All this will be done with Europa Clipper. Europa Clipper is on a so-called mega trajectory. Mega means mass, Earth, gravity assist. So we launched in October 24. We are right now on our way to Mars with a gravity assist that happens actually next month. And then we go back to Earth for another gravity assist. Then we have enough speed and power to go to the Jupiter system for a Jupiter orbit insertion in April 2030. Here's an animation, how this looks like when Europa Clipper enters the Jupiter system. Then we start a so-called pump down phase, meaning that Europa Clipper gets closer to Jupiter and gets onto a more stable orbit. Then we start the flybys on Europa. And I mentioned earlier that Jupiter has a very, very strong magnetic field and there's so many charged particles. And this is not only important for Europa, but also for the spacecraft, for Europa Clipper. So on the top right here on the slide, you can see a Geiger counter counting the radiation dosage that Europa Clipper is experiencing. So all this has to be accounted for. Yes. So let's wait for the animation to finish. And one of these instruments on board Europa Clipper will be able to analyze ice grains. That's a so-called surface dust analyzer, or short SUDA. It works in a similar fashion as the instrument on board Cassini worked. Ice grains on Europa can be emitted by, for example, plumes if they are there, or if not, then micrometeorites. So you have to imagine that Europa is not only bombarded by charged particles from Jupiter all the time, it's also bombarded by micrometeorites. And whenever these tiny micrometeorites impact the surface, they lift a lot of material and ice grains into Europa's exosphere. And with that, basically, an instrument like SUDER can just fly through that and analyze that material. And we know from Cassini that some organics and salts can be found in these ice grains if that material is detected by these instruments. But what we don't really understand yet is what actually happens in between the water source and and outer space when the material gets emitted into space. And for example, if you if you fly by a plume and you analyze that material, you can get information out of it. But we should be a bit careful with relating what we find directly to the ocean underneath for several reasons. So two of these reasons are that when the material freezes from the ocean, some compounds in the water can easier get into the gas phase or into the ice grains than others. All this affects the relative abundance ratios of these compounds compared to what is actually found in the water. On the other hand, when the material is formed and travels through these channels to space, as is the case on Enceladus, then some ice grains can maybe just stick onto the walls and get basically just removed from that stream. And all this affects how you should relate what you detect in the plume to the subsurface ocean. Because if you then put, let's say, we put bacterial cells into the ocean. So let's imagine there's life. There are bacterial cells. There is DNA. Maybe we find some fatty acids, whatever. Then you want to have the chance to find it. You want to get this material into these grains or some volatile stuff rather in the gas phase, and then you want to be able to detect it and relate it to the subsurface water ocean. So the point I want to make is that it is critical to better understand what actually happens when the water on Enceladus or Europa or any other ocean world freezes. So to better characterize and understand that freezing process. And one important thing, if you want to get organics or cells into such ice grains, is the phase state of these grains. This means if these grains are rather crystalline or if they are vitreous, amorphous, or glassy. That's three words describing basically the same. So crystalline means the water molecules form a nice crystal lattice. Amorphous, vitreous, or glassy means just the opposite, that there's no nice crystal lattice and the water molecules are there just in a very disordered state. Um, and one thing that controls that can control how much glass could be formed in these grains is the cooling rate, so how fast these grains actually freeze. And this is something else we don't really know yet. So if you freeze slowly, then cells can dehydrate, eventually lyse and damage. If you freeze fast enough, you may be able to vitrify these cells and maintain more of the and preserve more of these biological constructs, more of the cells or of these larger molecules. This process would be called cryopreservation. That is basically the preservation of a biological construct, a cell, DNA, protein, by cooling to very low temperatures. So what about Enceladus, phase states on Enceladus for Enceladus ice? The largest amorphous, so glassy signatures on Enceladus surface were found in the regions surrounding the tiger stripes. but freshly emitted material is predominantly crystalline. And then there are lab experiments showing that these ice grains, when they form, they may be able to contain both some crystals, but also amorphous phases. But we don't know how much actually of these grains is in a glassy state. And we wanted to address this question. So we were planning lab experiments with two different solutions. So our solution one had was more Enceladus relevant. It was more for an Enceladus ocean. Solution two was more relevant to other icy moons with more high salinity solutions. For example, Europa, if you imagine brine pockets in the ice shell. And then what we did is using these solutions, very tiny amounts, and then cooling these at different cooling rates, and then you can get some so-called thermograms out of it and analyze them and try to make sense of it. So the technique we use is differential scanning calorimetry, and this is a thermogram. I don't want to go into detail, but you can see that when things are crystallizing, you can see when things are melting, and you can get an idea if there is some glass in these compounds, and there's even we can even estimate the amount of glass relative to the amount of crystals that were formed. And we did a lot of these experiments with different cooling rates, and that's basically what we get out of it. So there are a few things to note. The degree of vitrification means the amount of glass in the sample. This increases if there is more salt in the sample. It also increases if the cooling rate is higher. And for Enceladus ice grains, this means, depending on the cooling rate, which we don't really know right now, these ice grains can have about up to 5% glass or amorphous phases, which is well in agreement with what is found from Enceladus plume analysis. And then ice grains with higher salt concentrations, like maybe those on Europa that could form, they can have higher amounts of glass, like 15 to 35%. That's what we got. So we also found that when we tested different sample volumes, meaning ice grain size, this does not significantly affect the degree of vitrification. So coming from these lab experiments, where we are shown there can be some glass in these grains, and maybe it's possible to get cells or bacterial cells into these grains, coming from these experiments to another bunch of lab experiments. It's the last part of my presentation. So I want to go back to the lab setup that I mentioned in the beginning, that was used to interpret data from Cassini and give us a clue about the organics in the ocean or the salts in the ocean of Enceladus. But we can also use the same setup to predict future data that will be recorded by Europa Clipper, by the instrument on board Europa Clipper. Because you can go to the lab, you can measure whatever you want, and the instrument will then tell you how the data should actually look like if Europa Clipper would find similar components in the vicinity of Europa. And we did this with compounds that are interesting for the search for life. And for example, we have tested amino acids. And all amino acids here that we tested show us a very clear and distinct fragmentation pattern. So a clear pattern of peaks that allows us to say, yes, this was an amino acid. And also in the case of fatty acids, it's basically the same story. And here we could even differentiate between abiotic abundance ratios of fatty acids. This means without the involvement of life, and biotic abundance ratios. This means with the involvement of life. Okay, so far so good. But here we went to the lab and we mixed compounds together, and then we measured it. And then we want to go one step further. What actually happens with bacteria with real life? So I'm not a biologist, but I keep talking to biologists, and they said when you've never worked with bacterial cells and you want to get started with it, do E. coli. So that's what we did. And we also decided to test another species. There's this S. alaskensis, Sphingopyx S. alaskensis, because we believe they are probably a better analog for potential life on an icy moon like Enceladus or Europa for several reasons. So these cells, they like cold environments, they can live at very low nutrient levels, they utilize H2 as an energy source, and H2 was recently found, was found in Enceladus plume, for example. And they are very small, so they could, in theory, fit into these ice grains and then get emitted into space. So what we did is we took these bacterial cells, we extracted DNA from these cells and measured so how it should look like if an instrument like SUDA on board Europa Clipper would encounter ice grains with some traces of DNA in it. And this is one example spectrum. So on the top right, first of all, you can see a typical DNA molecule with the 4 nucleobases, adenine, thymine, guanine, cytosine, and the phosphate sugar backbone. And the mass spectrum that you see here clearly shows you 3 peaks that can be related to 3 of these nucleobases. And also there's another peak that can be related to the phosphate sugar backbone. Then we also extracted lipids, basically the membranes of these bacterial cells. And what we see in the mass spectrum is fatty acids, which are basically the small components of these lipids. So fragments, we see fragments of these lipids in very particular abundance ratios. And we can not only identify these fatty acids and these lipids in the mass spectra, we can also use it to differentiate between the different the 2 different species that we tested. Because there are clear differences between the spectra. For example, here in the case of S. alaskensis, there are more unsaturated fatty acids and there are more of these larger phospholipid fragments than in the E. coli case. So, and the next spectrum is the maybe most demanding case where we have not extracted anything and just measure the bacterial cell as it is to see what happens if an instrument like SUDA detects such a cell as is, just the cell in an ice grain. And the mass spectrum here looks very, very busy. And the large peaks here, they are not very spectacular because they are more features of water, potassium, sodium, a bit of NH4. But the smaller peaks here, they are more interesting. Based on all the experiments we did in the past and that I showed you with amino acids and fatty acids. So based on all our experience, we could relate some of these peaks to amino acids and also to metabolites of the bacterial cells. So metabolites are products in the bacteria's metabolism. And here, that is a cation spectrum. So what you see here is the positively charged ions that were generated in the lab setup. Here are the negatively charged ions. That is the anion mass spectrum. And again, here you can see fatty acids. Again, these lipid fragments in very particular abundance ratios. We have then also lowered the cell density, so basically the concentration of the cells in our samples for 2 reasons. So one reason is you want to make sure that the features you see are definitely from the bacterial cells, because if you lower the concentration, these features should get lower and at some point they should vanish, and this worked. And then you can also determine the detection limit. So how much do you still need of a bacterial cell to find it with such an instrument on board Europa Clipper? And if we relate our results to ice grain detections on Europa or in the future maybe Enceladus, then we find that even very tiny traces of these cells could be identified if they really care about getting incorporated into these ice grains and then ejected into space. Come on. All right, so that's the last slide I have. That's just a summary of all the species that we identified in the mass spectra. So I will not name all of them, but I hope this is somehow convincing that we can find such bacterial cells with these instruments like SUDA on board Europa Clipper. And then that's my take-home slide. So just to summarize, the 2 moons Enceladus Europa are among the best places to look for alien life in the solar system. There are definitely other places, but Europa and Enceladus are among them. Then I also showed this ice grain mass spectrometry is a very good technique for astrobiology investigations. You definitely always need lab experiments for detailed analysis or prediction of data of these instruments. I also showed when ice grains form, then the more salt and the faster they freeze, the better it is to preserve organics or cells in these grains. And signatures of these organics or bacterial cells can be identified at very, very low concentrations if they exist in an ice grain. And with that, I say thank you and look forward to your questions.